Okay, we're back to finish up our last two examples for conservation of momentum. Example number 2. A golf ball of mass 0.05 kilograms is fired at a stationary 6 kilogram bowling ball with a velocity of 45 meters per second. If the bowling ball moves after the collision with a velocity of 0.7438 meters per second, what is the velocity of the golf ball after the collision, and was energy conserved? So this one's a little tough to see because they don't really tell you directions, but let's just think about it logically. You fire a golf ball at a stationary bowling ball. It doesn't tell us the directions, but I think we can pretty safely assume that the golf ball's initial velocity, when it hits the stationary bowling ball, it's going to make the bowling ball move in that same direction. Okay? We don't know yet whether the golf ball ends up moving in the same direction, but that is what we can find out. That's what we want to find out. We want to know the velocity of the golf ball after the collision. So first, I would say let's define our system. I think it's pretty obvious we should use the golf ball and the bowling ball together as our system. That way any forces between them we can discount as counting towards the net force because they're internal forces. There are no other forces acting on these two objects from the outside, so we can assume that momentum is conserved. So we start off with, as normal, P naught equals P. Now we have two distinct objects both before and after the collision, so we're going to have two different terms on each side. And let's see, direction. Let's make the direction that the golf ball is initially moving in positive. I'm making the assumption that, and I think it's a fairly safe assumption, that the bowling ball after the collision is going to move in the direction the golf ball was moving in, so that velocity will also be positive. And we're given information about the masses and the velocities, so that means that we can go right down to that level when we're writing out our momentum terms. Remember, momentum is mass times velocity, so initially we have two objects to account for, so I'm going to write m1 v1 naught plus m2 v2 naught equals m1 v1 plus m2 v2. Now, initially, the bowling ball, let's call that m2, is stationary, so this term right here is going to completely cancel out, and that's 0. Now, all we have to do to find the velocity of the golf ball after the collision, that's v2, is the golf ball is v1. The velocity of the golf ball afterwards is v1, my mistake. So now all we have to do is plug numbers in. Golf ball is object number 1, so the mass is 0.05 kilograms. Initial velocity, 45 meters per second, equals 0.05 kilograms v1 plus, here's the 6 kilogram bowling ball, 6 kilograms, and that is now moving at 0.7438 meters per second. Now it's just math. Make sure you do the math correctly. Okay, the rules of algebra should be pretty straightforward by this point. So that's 2.25 equals 0.05 v1 plus 6 times 0.7438. That would be 4.4628. So just so everyone's clear on what I'm going to do, I'm going to take this number, subtract it over to this side. So 2.25 minus 4.4628. I get a negative number, and I divide that by 0.05, and it turns out that v1, the final velocity of the golf ball after the collision, is negative 44.256 meters per second. Okay, now what does that negative mean? Well, we took the positive direction to be the direction that the golf ball was initially moving in. This means that after it hits the bowling ball, it must be moving the other way. And I think if you imagine that scenario in your head, that kind of makes sense. So I'm just going to put in parentheses backwards. There we go. We are also asked once again if kinetic energy is conserved this time. So again, we'll write out our K naught equals K. I'll put a question mark there. 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 squared plus 1/2 m2 v2 squared. I know that initially the bowling ball, is not moving. This term will cancel out. That means I also have a whole bunch of 1/2s, a 1/2 on each term. So I'm going to cancel those as well. If I divide each term by 1/2, they'll all evenly cancel out. So I have 0.05 kilograms times 45 meters per second squared equals 0.05 kilograms times negative 44.256 meters per second squared. I'm going to run out of room here. Plus 6 kilograms multiplied by 0.7438 meters per second squared. Okay, now it's time to do the math. 45 squared is 2025 times 0.05 is 101.25. Negative 44.256, there's the negative. We're going to square that. A little bit under 2,000 times 0.05. We get 97.93, we'll call it. Plus 0.7438 squared times 6. Let's call that 3.32. Okay. 97.93 plus 3.32 equals 101.25. So yes, I was rounding a little bit, but you can see that there's such strong agreement that it's pretty obvious that this was meant to be an example where there is conservation of energy. Okay? So we see that in some cases, such as in the last video, energy is not conserved. We also see cases where it is. Let's move on to example 3. This is a little bit more typical where you're going to have to mix ideas of both conservation of energy and conservation of momentum. Two blocks, one of mass 15 kilograms and the other of mass 6 kilograms, are tied together by a string. A spring is then compressed between the blocks. When the rope is cut, the more massive block moves off with a velocity of 9 meters per second. What must the velocity of the less massive block be? So here's what we got. We have a block of 6 kilograms tied to a block of 15 kilograms, and there's a spring between them. Okay? Now, the spring is compressed. When it's not like attached into the blocks, it's compressed and then put between them. When the string is cut, it's going to allow that spring to decompress, to lengthen, and push those blocks apart. So this is not a collision so much as this is an explosion, per se. But we do know that in our system, if our system consists of the blocks and the spring, then there is no net external force. If we were to just say the blocks, then you would say, yeah, there's a spring pushing on them. The spring provides the net external force. But if we include the spring, and I know it doesn't say this, but the spring, let's assume that it's a massless spring. We usually deal with massless springs in this class. If it's a massless spring and we include the spring in the block spring string system, then there is no external net force on any of these objects, and therefore momentum is once again conserved. And we can write this. Initial momentum equals the final momentum. Now, as far as the objects that are moving, that have mass, that have momentum, before the collision there are two separate objects. After the collision there are also two separate objects. So I can start off with this, m1 v1 naught plus m2 v2 naught. Oh, and we have information about masses and velocities once again. Equals m1 v1 plus m2 v2. We're not told directions like left, right, east, west per se, but we are told that the more massive block moves with a velocity of 9 meters per second. So this more massive block is going to move to the right. For the sake of doing this problem, let's call that the positive direction. So the direction that the 6 kilogram block moves should be negative. So we expect in our math, the math to work out so that our final answer for the velocity of the less massive block is negative. Now before the string is cut, everything in this system is at rest. So that means there's no initial velocities. Both these terms cancel out, which is interesting because that means that there is no initial momentum. Yet both of those blocks are going to end up moving. So what does that imply about the momentum of those two blocks? It implies that even though they are both moving and individually they both have momentum, because one of them has negative momentum because it's moving in the negative direction, we already specified positive and negative directions, that the momenta of the blocks is such that it cancels out to still be zero. Because if there's no momentum before the explosion, there can't be any momentum after the explosion. So, starting to plug numbers in, m1 is 6 kilograms times v1 plus the 15 kilograms times 9 meters per second. Okay, I'm gonna move this term over to the other side. So I have negative 6 v1 equals 15 times 9, 135. And I divide the negative 6 over, not that, there we go. And I end up with negative 22.5 meters per second. I'm just going to put in parentheses opposite direction. Now, does that make sense? Does it make sense that since we talked about both of the blocks having the same momentum, does the smaller one have to have a bigger velocity? And the answer is absolutely yes, it does. That's how we get the same momenta out of both of them. Okay, so the 6 kilogram block moves off with a speed, a velocity of negative 22.5 meters per second. Now the second part of that question is where we start to tie in the energy. Don't forget about the energy stuff just because we're off of that unit. It's still going to be important. If the spring that caused the blocks to move apart was compressed at 0.6 meters, what is the spring constant of the spring? Can't solve this with momentum, okay? We're saying for the sake of this problem that the spring is massless. It's not included in any of these terms. But we know that we can deal with this because we know about another conservation law. We know about the conservation of energy. Where was the energy at the end of this problem? It was stored in the two blocks that were moving. Well, where did that energy come from? It was all stored in that spring. The spring is where the energy was stored. When the string was cut, the spring gave the energy to the two blocks. So, our criteria for telling if energy is conserved is to see if work was done by an outside force. And since our system consists of the spring and the two blocks, well, the energy is already included in there. So no outside force did any work. So we can go right to our statement of energy conservation. ET equals ET. Left-hand side is for initial. Initially, nothing is moving, but there is elastic potential energy. So I'm going to write down USO for initial elastic potential energy. At the end, once the spring has pushed the two blocks out, now the spring doesn't have any elastic potential energy anymore, but the two blocks are moving. So there is some kinetic energy, K. All right, let's take this one step further. The equation for elastic potential energy is 1/2 kx squared. And then we have two objects that are moving, so we do need to write 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Once again, notice that I have a 1/2 in every single term. That means I can divide both sides by 1/2 and get rid of all of those. Okay? That's totally fine, totally acceptable to do. Now I'm trying to solve for k. Do I know what the x is? Remember, x is the compression or elongation distance. I do know what that is. It's 0.6 meters. And I already know the masses and velocities, one of which I just solved for. Now this just becomes a plugging in problem. 0.6 meters equals 6 kilograms. Remember the speed the velocity we just found is 22.5 meters per second squared. Negative, but that negative is going to cancel out because we're squaring it, plus 15 kilograms times 9 meters per second squared. Okay, so if we do 22.5 negative, we're going to square that. We're going to multiply that by 6. And to that, we're going to add, let's see, 9 squared is 81. So we're going to add in parentheses 15 times 81. Okay. And now we're going to divide by 0.6 and divide by 0.6 again. And we come up with a spring constant of a very high spring constant, actually. 11,812.5 newtons per meter. This is an extremely stiff spring. That means it takes over 10,000 newtons, to compress the spring, of force to compress the spring and hold it at a compression of 1 meter from its normal length. This is an extremely high spring constant, okay? Very, very, very high. But it is reasonable. There are objects with spring constants that high. So it's not outside the realm of possibility. But that just shows us, and it has to be that high because we're creating a lot of kinetic energy here. We're moving fairly heavy objects fairly quickly. It might not sound like it to you, but 22.5 meters per second is I think roughly on the order of somewhere between 40 and 50 miles per hour. That's very, very fast. Okay, I would think that most of us might be able to at our top speed to throw a small object at that sort of rate, and this is a 6 kilogram object. So there's a lot of energy stored here. And in order to store that much energy, we need a very high spring constant, okay, that can help us store out that much energy in the spring. So this is an example of how we take energy and momentum and can use them together. There's many other examples that we'll do in class that you'll do on homework, but I just wanted to give you a taste of it for right now. That is actually the end of the notes on momentum. I'll be back with you when we start talking about simple harmonic motion. Until then, I'll see you later.